Okay, I think maybe we could get started. Today we will have Grigory Bartosh from the University of Amsterdam in the machine learning group, machine learning lab, to talk about SDE matching. Thanks for your joining, and let's get started.
Okay. Yeah, thanks guys for having me. It's an honor. Okay, so yeah, today I'm going to present the SDE matching. It's the work we submitted and going to publish at ICML 2025 with my colleagues Dmitry and Christian. And I would like to start from some very, very high level intuition. So, and the method I'm going to present is based on diffusion models, has a lot of connections with them. And let me start my presentation from diffusion models as well. So diffusion models, so how they work, they start, if we want to generate image with the diffusion model. So we start from an image which is full of noise. Then we run some stochastic trajectory that returns, that ends up in image in a point from distribution of images. Yeah. So this is how it looks like. However, intuitively, we may think here, so if we want to generate not one image, but a sequence of images, yeah, so why should we stop here? Why couldn't we just somehow continue our our trajectory and generate the next image and then a next image? Okay, and in this way, potentially, we could generate a distribution of videos. So this example is very, very simple. So of course, well, in this way, we can generate just videos where next image only depends on the previous one. And this will be a very simple distribution of images, but still, yeah, potentially it's a way to enrich the family of diffusion models. Okay, so and yeah, in this work, we I present the way how we can construct something very similar. Okay, so okay, but first, let me introduce diffusion models slightly more formal, in slightly more formal way. Okay, so in diffusion models, we have two processes, the forward process and the reverse process. So the forward process takes a point from a data distribution and step by step inject noise, destroy the information. And the reverse process, it goes in the opposite direction. It starts from some simple distribution and step by step remove noise and reconstruct the information. Okay, so in continue, we can formalize the forward process as following. So we say that we have some data point X. We start from a simple distribution Z0 given X. Yeah, this distribution is usually just very close to the data point itself. And then we run a very simple stochastic differential equation that goes forward in time, and at time point 1, we have some simple distribution. Usually it's a unit Gaussian distribution. So this is the forward process. This process, again, takes the point and destroy all the information. Okay. So this forward process has a property that at any time step t, any intermediate times t, time step from 0 to 1, we have access to distribution of this variable, latent variable zt, given X. Okay, and this distribution is a simple Gaussian distribution with some mean function which is just scaled X and some very simple covariance matrix. Okay, so if we marginalize this conditional distribution, we may find an unconditional, the marginal distribution of latent variables. Okay, and this is how it looks like. So again, for one point X, it looks like this. So, and for the entire data distribution, the distribution of latent variables and intermediate time steps, well, this is how it looks like. Okay, so, and what we want from diffusion model, we want diffusion model to generate trajectories that starts from this simple data distribution and end up somewhere here at our data distribution. Okay, so, and the trick is that if we have the forward process, the forward stochastic differential equation that looks like this, so the only thing we need is so-called a score function. It's a gradient of the log probability of the marginal distribution of latent variables at each time step. Yeah. So if we have the forward SDE, which we do have, and somehow we know this score function, so we can construct the reverse process that goes backwards in time. Okay. So to find this score function in diffusion models, so we would like to minimize objective like this, where function S is approximation of the target score function. Okay, and yeah, we just know that this objective can be rewritten like this. So instead of this score matching that we, of course, cannot do because we don't have the targets, so we can do conditional score matching, where we match our function S with the conditional score functions. And due to the simplicity of the forward process, we have analytical access to these conditional score functions, because again, this conditional distribution of the forward process is very simple. Okay, any questions so far? Okay, yeah, then let's continue. So the two main points here are that this conditional score matching, we can show that it's a variational bound on model's likelihood. And this conditional score matching objective, it's a simulation-free objective. So when I say it's a simulation-free, I mean that we do not need to numerically simulate anything during the training. So when we do the training, we don't need, for example, to numerically integrate this forward process. This forward process is simple, and we can just generate samples ZT by sampling from this simple Gaussian distribution. So we don't need to run some numerical solver of this stochastic differential equation. Okay, and this is a very important property of diffusion models. Okay, so that was about diffusion models. And now I would like to talk about latent SDE. So latent SDE is a very flexible, very powerful framework for time series modeling, and it has a lot in common with diffusion models. And in a couple of minutes, we will see what it is. So latent SDE. So in latent SDE, we have some latent dynamic in a latent space. So we have a time. For simplicity, let's consider the time from 0 to 1. And the latent process in this latent space, it starts from some prior sample from a prior distribution P of Z0 at time step 0. Okay, and then it runs dynamic forward in time. Until time step 1. So, and this dynamic is defined by some stochastic differential equation. So for the simplicity, again, I will only consider dynamics with this very simple diffusion terms that has form G times dW. So dW is a Brownian motion, simple Brownian motion, and G is just some coefficient. So in general case, this G can be also a function of state and time, but right now I'm gonna only consider this simple case. Okay, so this is the dynamic in the latent space. Oops. Okay. And then how we generate observations. So we simply take these latent variables in latent space at sometimes steps and sample observations from some observation model. Yeah. So this observation model can be, it's arbitrary. It can be anything. Okay. So in this way, we define the generative model itself. Okay, so we can generate like this some time series. Okay, and then if we have a set of observations like here x some t1, x t2, x1, so we may want to find a posterior process. So distribution of posterior trajectories. So two things about this posterior process. First of all, it exists. So if you know the some set of observations, so these 3 points, for example, so in theory, some conditional distribution of trajectories that could generate these 3 observations. So this distribution exists. It's untractable in general case, but it exists. And that was the first thing. And the second thing, we in latent SDE framework, we need this distribution of posterior trajectories to train the model. So let's discuss it. So we have this set of observations, and we have some conditional distribution at each time step. So at time step 0, we have some Q of Z0 given X, where X, this capital X is a set of our observations. Okay, oops, and then we have some conditional process that is conditioned on our observations X. Okay, so, and this process, it generates at each time step some conditional distribution of latent variables ZT given our set of observations X. Okay, and this process runs from time step 0 to time step 1. Okay, so this is the posterior process. So, and again, if we have some generative model that we discussed before, so we know that this posterior process, it exists. We just don't know what it is. So what we can do, we can parameterize it with some parameters phi. Okay, and then this is how we can train the latent SDE model. So we can write down a variational bound on model's likelihood, and it will have 3 components. So prior loss, diffusion loss, and reconstruction loss. So prior loss makes sure that both processes starts from kind of more or less same distribution. Okay, the diffusion term makes sure that the processes are somehow aligned. Yeah, so here we can see that the diffusion term is just some kind of expectation of squared norm of difference between drift terms in two processes. Okay, and the reconstruction loss, it makes sure that we can correctly reconstruct our observations. Okay, so the prior loss and the reconstruction loss, they're kind of simple. Okay, and the diffusion term is more complex. So let's take a closer look. So what we have here, so if we have some observations X, okay, we consider all possible trajectories, capital Z, so I use capital Z for entire trajectory. So this Q of capital Z given capital X is a distribution of trajectories given observations. Okay, so and inside we integrate from time step 0 to time step 1, yeah, and we integrate over this some trajectory Z, which is generated by conditional process, a conditional posterior process F. Okay, so and we calculate this difference. Okay, so of course I'm not gonna derive this objective right now, but that would be great if yeah I know that everyone understand what we should calculate here to find this objective. Okay, so any questions here? 3, 2, 1. Okay, let's move further. Okay, so this is the training, how we can train the latent SDE model. So again, we need to define the generative process, we need to parameterize it, we need to parameterize the posterior process, and then we can calculate this objective. So as I mentioned before, so the latent SDE itself, it's quite a powerful model. So it generalizes many things, including, for example, latent ODE, which is powerful model itself, but in contrast to latent ODE, where we have an ODE, so deterministic dynamic in a latent space, here we may have a stochastic dynamic. Okay, so the problem here is that to train this model, so as you can see from this objective, we actually need to integrate some stochastic differential equations. Specifically, we need to integrate the posterior process. So let's go back here for a second. So if we have a set of observations, so in our data set, so for example, we have a data set of some sequences, and we have one sequence from this data set, so our observations. So we actually need to simulate this stochastic differential equation. Okay, so and this is expensive, and we need to do this for each training iteration. So that's a problem. And yeah, we would like to, it would be great to do something with that, because then we potentially could scale this latent SDE approach, okay, to some higher dimensions. Okay, which is again complicated due to necessity of integration of this posterior process. Okay, so what can we do with this? So as you remember, we started this discussion from diffusion models, and I mentioned that the diffusion models, they have a lot in common with this latent SDE. And in diffusion models, we have very similar, very similar construction. So we also have two processes. We in some latent space. They defined by stochastic differential equations, and the objective itself looks similar. But in diffusion models, we do not need to simulate any different stochastic differential equations. So let's find this connection. So how actually it looks like, and then maybe we could, it will help us to use the machinery of diffusion models to train latent SDE model more efficiently. Okay, so let's look at diffusion models. So again, in diffusion models, we right now let's look at the forward process, that destroys information. So in diffusion models, we have some observation X, so our data sample, and we sample start from Z0, then we go forward in time, and at each time step we have some distribution of latent variables given our observation. Okay, so to find this connection between diffusion models and latent SDE, let's do some manipulations with this diffusion models formulation to find the connection with latent SDE. So first, let's inverse the time axis. So previously, we said that forward process goes forward in time. Now I'm saying that forward process will go kind of backwards in time. And at the same time, I invert the time axis. So now it still goes forward in time, but I inversed the intermediate distribution of latent variables. Okay, so, and this intermediate distribution of latent variables, so they are still simple, they're still tractable. However, the stochastic differential equation that previously defined the forward process, it now goes backwards in time. So it kind of starts from Z1 and goes to Z0. Okay, but so if we want a stochastic differential equation that goes forward in time, so, well, we need to do the same trick that diffusion models do for the marginal process, but for the conditional process. So we need to use a score function to define, to inverse the time of this stochastic differential equation. So now we will have this stochastic differential equation that goes forward in time, but instead of marginal score function, here we use only conditional score function. Okay, so is it clear, these manipulations? Any questions? Okay, I don't see any questions. So let's continue. Okay, so, and yeah, the last thing here is that I'll introduce an observation model, which in case of diffusion models, it will be super simple. So we just take our Z1 and sample observation X, which is, I don't know, somehow very close to Z1. Okay, that's it. So yeah, so with these manipulations, we can kind of transformed the definition of diffusion models to bring it to the terms of latent SDE. Okay, and let's now take this specific, very specific posterior process with only one observation and substitute it into the objective of latent SDE. Okay, so this is objective of latent SDE. So, and now let's substitute what we what we just derived. So first of all, prior and reconstruction losses. So we don't need them because in diffusion models, usually the forward process constructed in such way that these terms are negligible. So now the diffusion term. So in diffusion term, first of all, we don't have any parameters in the forward process. So slightly simplifies the thing. So, and yeah, we have here inside just this score function, a conditional score function, and some function as theta. So, and this kind of makes sense, yeah, because previously we saw this objective, and I mentioned that this is a variational bound on models likelihood for diffusion models, and here we have the same objective. Yeah, so again, we took some variational bound on models likelihood in terms of latent SDE, substituted the posterior process from diffusion models, and voila, we have exactly the same objective. Okay, so this gives us, again, the connection between latent SDE and diffusion models, and illustrates that the objectives in diffusion models is actually a variation bound on models likelihood. Okay, so is that clear? So this step? Okay, cool. So yeah, we have this form of diffusion model objectives I'm sorry, diffusion loss. So, and one more thing is that now we can switch the order of integration and expectation here. So yeah, and this allows us to simplify the diffusion loss further, because instead of first inferring the entire trajectory z given x and integrating whatever we have inside from time 0 to times 1, we can kind of first define what time step we're interested in, and then yeah, taking the expectation. So which means that inside we don't need the entire trajectory z, and we only need some zt, some latent variable distribution of latent variables at specific time step t. Okay, and this significantly simplifies the objective. Okay, so now instead of numerically simulating the posterior process, we can simply, yeah, sample time, time step t, sample latent variable zt from this conditional distribution, okay, and calculate this, whatever we have inside under the expectation. Okay, and that's it. So in this way, we can construct a Monte Carlo estimator of this expectation. Okay, so, and this is way simpler problem. Okay, so, okay, so, so now we see the connection between latent SDE and diffusion models. So, but of course, so what we have in diffusion models is way simpler setting rather than what we have in latent SDE, where the posterior process is some complicated dynamic defined by some stochastic differential equation. Okay, so, and the question is, what can we do here? How can we do the same trick where we yeah, just sample time, sample latent variable zt, and evaluate and estimate the diffusion loss, yeah, without without simulating the posterior process numerically. So that's the question. And the answer is, well, we can construct such posterior process where we have access to this this conditional distribution ZT given X, and this is the only thing we need. Okay, and let's look how we can do this. So this is the idea from our previous work, neural flow diffusion models. So, and I'll try to quickly explain it here. Okay, so what we're gonna do, we are going to introduce a reparameterization function f that takes us some noise epsilon from a simple distribution. In this case, it's just a unit Gaussian distribution. Then conditionally on observation x and time step t, function f transforms this noise epsilon into our latent variable zt. Okay, so here's an illustration. So we can take a sample epsilon from this simple unit Gaussian distribution and apply transformation f. And in this way, implicitly, we define the distribution of latent variables zt given x. So this this distribution, it depends on reparameterization function f. Okay, and it may be a quite complex distribution. Okay, and we can do it at every time step. Okay, and in this way, we again implicitly define a series of probability distribution from time step 0 to time step 1. Okay, again, in this way, we define implicitly a series of probability distributions zt given x. Okay, so what's next? Next, we can define a conditional ordinary differential equation that follows this given series of probability distribution. So how can we do this? We can do it as following. So let's take this noise epsilon that we used before, and let's fix it for all time steps. Okay, so, and then we apply our function f for this noise epsilon at every time step. In this way, we will have a trajectory. Yeah. So if our reparameterization function f, capital F, is continuous, then continuous and well, differentiable with respect to time, yeah, we will have a smooth trajectory in latent space z. Okay, so formally we can write it down like this. So we introduced, some function f bar that defines the ODE, and this f bar, how we can find it? We can just differentiate reparameterization function capital F with respect to time. Okay, so this is the trick. Any questions here? Okay, so okay, in this way we define the conditional ODE. Okay, and yeah, so it may look like this. So it may start from some narrow distribution and up in this wider distribution. Okay, and in between it can be just something. Okay, and the last step to construct this posterior SDE, because this is what we need. We need posterior stochastic differential equation that is conditioned on our observations. So yeah, is to transform this ODE that we just constructed into a stochastic differential equation. So, and how we can do this? So again, we can use the same trick with the score function. Yeah, so we can take this ODE that we had before. I'm sorry, it should be bar here. So, and yeah, we add this additional term that contains the score function and squared the volatility function. So here it is. Yeah, so yeah, if we know this score function of conditional probability distribution Q of ZT given X our observations, so we can switch from OD to SDE. Yeah, so again, let's repeat that this reparameterization function capital F that we introduced, it first implicitly define the probability path. Then, based on the same function, we derived an OD that goes through this probability path. Okay, and then lastly, we construct a stochastic differential equation that follows exactly the same probability path of distribution QZT given X. Okay, so, and this is how we can construct the posterior SDE. And yeah, importantly, so if we have some ODE and have some probability path, then no matter what volatility function we have here, we will always have exactly the same probability distributions of latent variables in between. Okay, so this is this thing I wanted to emphasize. Okay, cool. So using this idea with the reparameterization function, we can construct a posterior process in such way that we have access to both the this conditional probability distribution ZT given X and the SDE that follows this series of probability distributions. Okay, so we can now parameterize the posterior process, so which gives us access to both these things. Okay, so again, previously we directly parameterized this posterior SDE, so we didn't have access to this conditional distribution, and now we do have access to this distribution. Okay, so this is the benefit. Okay, so, and yeah, now, while keeping exactly the same generative model, we can use a different parameterization of the posterior process, which allows us to train the entire latent SDE model more efficiently. Yeah, so we keep exactly the same variational bound on model's likelihood. We keep exactly the same prior and the reconstruction terms. So the only thing we do, we reparameterize the posterior process, and this allows us to rewrite the diffusion loss in the way that we can efficiently estimate this expectation without simulating the posterior process numerically. Yeah, this is the benefit. Okay, so yeah, because as we discussed before, regular diffusion models, they are just special case. The regular diffusion model is a special case of latent SDE. So then it means that we can construct, using the same idea, we can generalize diffusion models in such a way that the forward process in diffusion models is now more flexible. So this is what we did in our previous NFDM work, and it allows us to learn diffusion models with that has generated trajectories with some special properties. Like here, we can construct a diffusion model where deterministic trajectories are straight line, for example. So we can also construct bridges between two distributions. This is a special case of latent SDE model with two observations. So regular diffusion models is a special case where we have just one observation at just one time step. Bridges, diffusion bridges, we can see as a special case where we have two observations at two different time steps. Okay, and we can, of course, use this technique to construct bridges between distributions. Okay, and yeah, in more general case, of course, we can do what latent SDE model is meant to do. We can model the time series, distribution of time series. Yeah, so here you can see a simple example with the stochastic 3D Lorentz attractor. So yeah, the distribution of trajectories looks like this. So this is just a visualization of data distribution. So we have some kind of sparse observations. So, and this is what model can learn. Yeah. Okay, and the benefit of the technique that I just described that we call SDE matching is that most importantly, we now have asymptotically cheaper training procedure with just capital O of one memory in time at each training step, where previous techniques usually required numerical simulations of the posterior process. So they have some they're more expensive in memory and time, asymptotically more expensive. And also, this is just empirical observation that SDE matching, it converges faster. We believe that this is just due to more efficient parameterization of the posterior process, and because it's easier for the model to learn the correct trajectories if we directly parameterize the posterior process with this reparameterization function. Yeah. So, okay, yeah, and also the final thing is that we see that with SDE matching, in contrast to adjoint sensitivity method that requires numerical integration and backpropagation through the numerical integration of posterior process, we basically have more stable gradients. Yeah, so because we don't need to backpropagate through this many steps of numerical integrator of SDE, we have more stable construction. Yeah. So yeah, and you can see here, that we do have low variance of gradients and low magnitudes of gradients. Yeah. Okay, and just a final example is that adjoint sensitivity compared to SDE matching, it just takes way more time to train the model, so it's difficult to scale the latent SDE model with adjoint sensitivity approach for training. Yeah, and for example, for this very simple video distribution of moving pendulum, after almost a day, or yeah, even more than a day, training on a single GPU, this is what adjoint sensitivity gives us, while SDE matching can burst way faster. So in just 20 minutes to 1 hour, so we can model a sequence of images of moving pendulum. Yeah. So yeah, I think that's it. If you have any questions, I will be happy to answer. Yeah, this is the end of my presentation.
Thank you. So if anybody have any questions, feel free to ask here. Maybe I will go first. So my question is, can you talk about like some detail, like how do you train this neural SDE? Because my impression is that you need two networks. The first one is the drifter that drift your latents in the SDE, and the second network is your normalizing flow, your conditional normalizing flows that transfer the observation to a bunch of samples, latent samples at a specific time t. But my impression is that because this is something like you have observation and you have a normalizing flow that goes to kind of a manifold, and you run the SD over the manifold. But if this manifold is changing like frequently, so would this introduce instability?
Mhm.
Or do you do something like to somehow prefix the latent space? For example, like pre-train on using a VAE to get some initial latents.
Mhm. Okay. No, we don't do any pre-training. So how we train the model? So, okay, from the beginning, yes, we do need two models to parameterize the unconditional and conditional, aka posterior process. Yes. So we parameterize the unconditional generative model directly, as we usually do in latent SDE. So, and we parameterize posterior process, yes, with this reparameterization function only. Yeah. So when I write here, so f theta, so I mean that we calculate this f theta through this reparameterization function. Okay. So then back to you next. Yeah, your question regarding the manifolds and rapidly changing distribution defined by this function capital F. So if it lies or not on a manifold, it depends on you. So how you parameterize this function F. For example, in our cases, in our experiments, if we work with the, I don't know, d-dimensional latent space, we use d-dimensional base distribution as well. Yeah, so we don't restrict ourselves to a manifold here. Okay, so if this reparameterization function f is a very sharp function, so, or yeah, we have some specific parameterization which leads to instabilities, then of course, yes, we will have unstable training procedure. But yeah, again, this is up to a user. Yeah, so if we should wisely choose how we parameterize this function capital F. So we don't introduce some unwanted instabilities. Actually, in our experiments, I can't say we have a lot of instabilities. No. Yeah. I can, of course, think about some very specific parameterizations, but in general, no, I wouldn't say we have a lot of instabilities here. What I think I should emphasize that most of our experiments, in most of our experiments, we use quite simple parameterization of this function capital F that gives us a Gaussian distribution of latent variables. This conditional distribution here, QZT given X is Gaussian. So I would like to emphasize here that it doesn't mean that this posterior process is kind of simple process. No, it still can be a complicated nonlinear process, but this is the restriction that we have. We also have an experiments where this real parameterization function f is some normalizing real NVP based flow. It works as well. Yeah. May it lead to instabilities? Yes, it may, but in our experiments, we don't see a lot of them.
I see. I see. So you don't need to like so you just train these two network jointly together.
Jointly, end to end, yes.
Okay. See, thanks.
Okay. Any other questions?
Yeah. Does anyone have any question to ask?
Grigory?
Yep.
I don't have questions. Very interesting work. Could you go to the final pendular radio case?
Yep.
So here what training data is used here? Like I assume the training data is a bunch of like pendular moving videos. And like have you done any experiments about what will the result look like between, for example, time equals to 0 and time equals to 1, like those intermediate frames? So it will follow the dynamics of the training data.
I think yes. Yeah. So I don't have visualizations right now, but yeah.
So how does it happen? Like, because I think if you in your training data you don't have any observation over those like intermediate states, so is it your like posterior models produce that, or how does it happen?
Yeah. Okay. So you're right. So we indeed have some discretization in our data set. Yeah. So we only observe pendulum at specific time steps. I don't actually remember the grid, the specific grid. So I believe, if I remember correctly, so this is a simulation of some real pendulum with 15 frames per second sampling frequency. So it's kind of frequent. Models simply interpolate between consecutive time steps. So we see something realistic in between. However, you're right. So if we have quite sparse observation of some real dynamic without any prior constraint, indeed, model may potentially learn something non-realistic in between. That's completely true. Yes. But I think it's always the case in any time series modeling approach. So yeah,
I see.
You can't do anything with that.
Yeah, it makes sense. Thank you.
Yeah, maybe we will call it now if nobody
Okay.
have questions. Okay. Okay. Thanks for your joining, Grigory. Thanks.
Okay. Thanks for having
See you guys.
you
Yeah,
guys.
see you.
So, thanks.